Right now, a machine the size of a tennis court is floating 1 million miles from Earth in the eternal silence of the void. This $10 billion masterpiece, which took 20 years to build, is currently capturing light that has been traveling through the darkness for over 13 billion years. It has just uncovered galaxies that were already fully formed only 290 million years after the Big Bang. How is it possible for something so complex to exist when the universe was still an infant? Are the very laws of physics we have spent centuries refining about to be rewritten? The James Webb Telescope is not just a piece of technology. It is a time machine. Its massive mirror, made of 18 gold-coated beryllium panels, unfolds like origami in the deep freeze of space to catch ancient, invisible light. Unlike previous telescopes that orbited our planet, Webb circles a specific point in the cosmos, known as the second Lagrange point, where gravity balances perfectly to keep it steady. From this lonely outpost, it stares into the infrared spectrum, seeing through clouds of dust that once blinded us. When we look at the images Webb sends back, we are not looking at the universe as it is today. We are looking at a ghost story, because light takes time to travel. A galaxy 1 billion light-years away is shown to us exactly as it appeared 1 billion years ago. Webb is pushing this reach to the absolute limit, capturing photons that began their journey when the universe was less than 5% of its current age. What it found in that darkness has left the scientific community in a state of shock. Standard models of the cosmos predicted that early galaxies should be small, dim, and disorganized. Instead, Webb revealed massive, bright, and mature structures that simply should not exist yet. One astronomer remarked that these discoveries might break cosmology entirely. We expected to find a nursery of newborn stars, but instead, we found a universe that was already wide awake and full of giants. In the vast, inky blackness of the early universe, astronomers expected to find only chaos and small, faint clusters of stars. But when the James Webb Telescope focused its golden eye on a tiny red smudge in a region of space now known as Jades, it discovered something that defied all logic. This galaxy, barely more than a speck in the telescope's first deep field images, turned out to be a record breaker that should not exist. When scientists ran the numbers, the results were staggering. The light from this galaxy had been stretched by a factor of 15, meaning it existed just 290 million years after the Big Bang. To put that in perspective, our universe is 13.8 billion years old. This galaxy was already shining when the universe was at only 2% of its current age, at a time when reality was supposed to be a dark nursery of simple gas clouds. Jades was already a sprawling metropolis of stars, spanning more than 1,600 light-years in diameter. Jades is not just an outlier. It is a direct challenge to our understanding of history. Standard cosmology says that galaxies are supposed to grow slowly. They should start as tiny clumps, gradually pulling in ki and merging over billions of years to become massive. Yet, Jades did not follow this script. It is too bright, too organized, and far too large for such a young age. Finding this galaxy so early is like finding a fully grown adult where you expected to see a newborn infant. It radiates the intense light of young stars, rather than the concentrated energy of a black hole, making its existence even more puzzling. It suggests that star formation in the early universe was far more efficient and rapid than anyone ever dreamed. This discovery has effectively pushed our view into cosmic history 40% further in just 18 months of observation, leaving us with a puzzle where the pieces simply refuse to fit together. The discovery of galaxies like Jades has forced scientists to look at the early universe with a sense of profound wonder and confusion. If the standard rules of cosmology were a simple clock, that clock seems to have been ticking much faster than anyone ever imagined. Before the James Webb Telescope, our best models suggested that the first billion years were a slow and steady climb toward complexity. We believed gravity needed immense amounts of time to pull gas together into the massive, swirling structures we call galaxies. However, Webb has revealed a different reality. In every direction it looks, it finds impossible structures. These are not just small, disorganized clusters of stars. They are mature, luminous, and highly organized systems. One researcher described this shocking revelation as finding a fully developed city where you expected to see only a few scattered tents. The universe simply should not have had enough time to build these giants through the processes we thought we understood. How could these structures form so quickly? Some scientists propose that star formation was far more efficient in the extreme conditions of the infant universe. Others suggest that dark matter halos, the invisible skeletons of galaxies, might have collapsed much more rapidly than predicted. There is even the radical possibility that the Big Bang did not spread matter evenly. If some regions were born much denser than others, they could have acted as cosmic fast lanes, allowing galaxies to jumpstart their growth. But even these theories struggle to explain the sheer scale of what Webb is seeing. We are witnessing a phase of history that refuses to fit into our textbooks, a mystery that suggests the initial conditions of our entire reality might be far more complex than we ever dared to guess. To understand why the James Webb Telescope can see what no other instrument in history could, we have to look at the very nature of light and the universe itself. Most of us think of space as a static void, but the universe is actually expanding, and it has been doing so since the moment of its birth. As this expansion happens, it stretches the light traveling through it, a beam of light that began its journey billions of years ago as visible blue or ultraviolet light does not stay that way. By the time it reaches us, its wavelengths have been pulled apart, shifting into the infrared spectrum, a part of the light scale that is completely invisible to the human eye. This is where the legendary Hubble Space Telescope met its limit. Hubble was designed primarily to see visible light, and as it looked deeper into the past, it eventually went blind. The most ancient starlight was simply stretched too far for Hubble's cameras to detect. Webb, however, was built specifically to solve this mystery. It is an infrared specialist, designed to catch those long, tired wavelengths that have been traveling through the cosmos for more than 13 billion years. This capability is what makes Webb a true time machine. When it looks at a distant galaxy, it isn't seeing the object as it is now, but as it was when the light first escaped its stars. It captures photons that began their journey when the universe was less than 5% of its current age. By peering into the infrared, Webb allows us to look past the thick curtains of cosmic dust that hide the birth of stars and the formation of the first galaxies. It has opened a window into the cosmic dawn, a period of history that was once thought to be permanently lost to the shadows. The journey to witness the dawn of time was not just a scientific challenge, it was an engineering odyssey that pushed human ingenuity to its absolute limits. To capture the faint, ancient whispers of light from the first stars, we had to build a machine of unparalleled precision and scale a machine that cost $10 billion and required more than 20 years of tireless dedication to complete. This is the story of the James Webb Telescope's Golden Heart, a masterpiece of design that had to function perfectly 1 million miles away from the touch of any human hand. At the center of this marvel is a primary mirror so large and complex that it could not fit inside any existing rocket in its fully realized form. Instead, engineers designed it to unfold like a piece of cosmic origami once it reached the silent vacuum of space. This mirror is composed of hexagonal panels made of gold-coated beryllium. Beryllium was chosen for its incredible strength and its ability to remain stable in the extreme, bone-chilling cold of deep space. But the true magic lies in the gold coating. While gold is beautiful to our eyes, its purpose here is purely functional. It is the perfect material for reflecting infrared light, the very light that has been traveling for over 13 billion years to reach us. The stakes for this mission were higher than perhaps any other in the history of space exploration, because Webb was destined for a remote location known as the Second Lagrange Point, or L2. There would be no possibility of a repair mission if something went wrong. Unlike the Hubble telescope, which orbited close to our planet, Webb circles a point where the gravitational forces of the Earth and the Sun balance perfectly, allowing it to remain steady while looking deep into the past. This isolation meant that the deployment process had to be flawless. On Christmas Day of 2021, the world watched with bated breath as the telescope finally launched. For the 6 months that followed, engineers and scientists lived in a state of constant, quiet anxiety. There were exactly 1,044 specific mechanical actions that had to work with absolute perfection. A single failure in any one of these steps would have doomed the entire $10 billion mission, turning the world's most advanced telescope into a piece of expensive space debris. From the tensioning of the massive sun shield to the precise clicking of the hexagonal mirror panels into place, every single movement was a high-stakes gamble against the laws of physics. One of the most critical components of this precision is the telescope's ability to stay cold, to see in the infrared spectrum. Webb must be protected from the heat and glare of the sun, the Earth, and even the Moon. It is shielded by a sun shield the size of a tennis court, which provides protection equivalent to a sunscreen factor of 1 million. This allows the sensitive instruments on the dark side of the telescope to be cooled to just a few degrees above absolute zero. Without this extreme cooling, the telescope's own heat would wash out the incredibly faint signals from distant galaxies, like trying to see a flickering candle next to a blazing spotlight. Every instrumental activation was executed flawlessly. And finally, Webb opened its golden eye. It began to look deeper into the history of our reality than any machine ever created by human hands. The precision required for these observations is almost beyond comprehension. For example, the Jades deep field observations required more than 70 hours of total exposure time. During this period, the telescope had to remain perfectly still, pointing at a tiny patch of darkness to collect individual photons that began their journey when the universe was less than 5% of its current age. This investment of time and resources is immense, but the rewards have been transformative. Every hour of telescope time is precious, and every photon collected is a piece of a puzzle that is billions of years old, because of the flawless unfolding of its mirrors and the incredible precision of its cooling systems. Webb can see faint red smudges against the cosmic darkness that were once completely invisible to us. These smudges are not just points of light. They are the very first chapters of the story of everything. The golden mirrors of Webb have proven that humanity can build a time machine capable of looking back to the beginning of time. We are no longer just guessing at what happened after the Big Bang. We are witnessing it through the combined power of its massive mirror and its ultra-sensitive detectors. We are capturing the birth of the cosmos itself in exquisite detail. This engineering triumph has set the stage for discoveries that are currently challenging every textbook narrative we have ever written about the universe. While the golden mirrors of the James Webb Telescope allow us to see the shapes and structures of distant galaxies, it is another instrument entirely that reveals their true nature. To truly understand the universe, it is not enough to simply see an object. We must know what it is made of, how fast it is moving, and how old it truly is. This is the realm of spectroscopy, a sophisticated technique that allows scientists to split incoming light into its component colors, much like a prism creates a rainbow from sunlight. By analyzing this cosmic rainbow, astronomers can read the chemical fingerprints of the stars. Every element in the periodic table, from the hydrogen that fuels a star to the oxygen we breathe, leaves a specific mark in the light it emits or absorbs. These marks, known as emission and absorption lines, appear at exact wavelengths that never change. By measuring where these lines show up in the light Webb captures, we can decode the entire biography of a galaxy billions of light years away. This technique is exactly how Webb confirmed the record-breaking distance of the galaxy known as Jades. While it appeared as a faint red smudge in images, its true identity was hidden in its spectrum. Scientists found hydrogen emission lines that should have appeared in the ultraviolet range, but instead, they were observed in the infrared. The light had been stretched by a factor of 15 as it traveled through expanding space for over 13 billion years. Without spectroscopy, we would only be guessing at its age. With it, we have definitive proof that this galaxy existed just 290 million years after the Big Bang. But spectroscopy does more than just measure distance. It allows us to witness the very birth of the elements that make life possible. In the modern universe, stars are rich with heavy elements like iron, silicon, and carbon. However, the first generation of stars, which astronomers call Population 3, were different. They formed from the pristine, untouched gas created during the Big Bang, just hydrogen, helium, and tiny traces of lithium. These primordial stars have never been seen directly, but Webb is currently hunting for their unique signatures. The spectrum of a pure hydrogen and helium star would look fundamentally different from any star we see today. And finding one would be like finding the original ancestor of every atom in our bodies, in some of the most distant reaches of time. Webb has already found something unexpected. In the afterglow of a massive stellar explosion called a gamma-ray burst, an event that released more energy in 8 seconds than our Sun will in 10 billion years. Webb detected the chemical signatures of silicon, oxygen, and iron. These heavy elements were forged inside the heart of a dying star and scattered into space when it exploded. Finding these elements so early in cosmic history tells us that the universe began enriching itself with the building blocks of planets almost immediately. It proves that the physics of stellar death billions of years ago was remarkably similar to the physics we observe in our own cosmic backyard today. The power of spectroscopy also helps us solve the mystery of the little red dots. These strange, compact objects found in the early universe often show a dual signature that left scientists baffled. Their spectra display broad emission lines, which indicate gas swirling at thousands of kilometers per second around a hungry black hole. Yet, at the same time, they show narrow lines associated with the birth of new stars. Normally, these two things do not happen so intensely in such a small space. By splitting the light, Webb allows us to see this internal struggle, a supermassive black hole dominating its host galaxy, consuming gas so quickly that it stunts the growth of the very stars that surround it. Even closer to home, Webb uses spectroscopy to search for the ingredients of life in the regions where new planets are forming. By looking at the disks of gas and dust surrounding young stars, Webb has detected the unmistakable signature of crystalline water ice. This ice is a crucial reservoir, the very source that might one day be delivered to rocky planets to create oceans and support life. The spectrum showed distinctive absorption features that could only come from water molecules, arranged in a regular, frozen structure. Finding this ice in multiple systems suggests that water is a common ingredient throughout the galaxy, significantly increasing the chances that habitable worlds like Earth are not unique. Every spectrum Webb captures is a time capsule. It tells us not just where things are, but what they are. It reveals the heat of gas falling into a black hole at millions of degrees, the cold of water ice in a distant solar system, and the chemical composition of stars that died before the Earth was even born. Through this rainbow of reality, we are finally able to read the story of the universe in its own language. Line by line, element by element, we are witnessing the chemical evolution of everything. From the first sparks of hydrogen to the complex machines we use to look back at them. To understand where we come from, we must look back to a time when the universe was a place of profound silence and absolute shadow. This era is known to astronomers as the Cosmic Dark Ages. After the initial fires of the Big Bang cooled down, the universe was filled with a hot ionized plasma where light could not travel freely. As space expanded and the temperature dropped below 3,000 degrees, electrons and protons finally combined to form neutral hydrogen atoms. Suddenly, the universe became transparent, but it remained dark. There were no stars, no galaxies, and no observers to witness the vast cold clouds of gas that filled the void. This period of darkness lasted for hundreds of millions of years, but within that gloom, gravity was silently at work. It was pulling the pristine gas of the early universe into massive, dense clouds. Because there were no heavy elements yet, no carbon, no oxygen, and no iron, the gas remained hot. In our modern universe, heavy elements help cool gas clouds, allowing them to fragment into smaller, sun-sized stars. But in the beginning, only the most massive clouds could overcome the internal pressure of the hot gas to collapse. The result was the birth of the first stars, known as Population 3 stars. These were titans unlike anything that exists in our sky today, born from nearly pure hydrogen and helium. They were 50 to 500 times more massive than our home star. They burned with a fierce violet-blue intensity, shining hundreds of thousands of times brighter than the sun. These stars were the original engines of creation, the first objects to transform the universe from darkness to light. However, their brilliance came at a cost. Because they were so massive, they exhausted their nuclear fuel with terrifying speed. living for only a few million years before dying in spectacular explosions. When these stars died, they did something miraculous. They scattered the very first heavy elements into space. Every atom of carbon in your body, the oxygen you breathe, and the iron in your blood can be traced back to this first generation of giants. They seeded the cosmos with the materials required for future stars, planets, and eventually, life itself. The James Webb Telescope was designed specifically to find these elusive ancestors of the cosmos. While a single population 3 star is too faint to see across 13 billion light-years, Webb looks for the collective glow of many of them, shining together. We are already seeing tantalizing hints in a galaxy called GNZ11, which existed only 430 million years after the Big Bang. Webb's spectrometers have detected peculiar hydrogen emission patterns. These patterns match exactly what theorists predict for regions where population 3 stars are actively forming. Beyond just providing light, these first stars also change the physical state of the entire universe through a process called ionization. Their intense ultraviolet radiation began to split the neutral hydrogen atoms in the surrounding space back into protons and electrons. Each star created a bubble of ionized gas that expanded outward into the dark. As more stars and early galaxies formed, these bubbles grew and merged, eventually clearing the neutral fog that had filled the universe since the Dark Ages. By the time the universe was 1 billion years old, it was fully reionized, allowing light to travel freely across the vast distances we see today. We are currently witnessing the transition from a dark, simple universe to the complex, luminous one we inhabit. Through the golden eye of Webb, we are connecting directly to the first chapter of cosmic history. We are watching the very first sparks of light ignite in the darkness, and in doing so, we are seeing the beginning of our own story. As we peel back the layers of the early universe, we find that the cosmic dawn was not just a time of first light, but a time of monsters. While the James Webb Telescope was busy discovering galaxies that formed too quickly, it stumbled upon something even more unsettling: black holes that appear to break the very laws of physics we have spent decades perfecting. These are the overmassive black holes, and their existence is currently forcing astronomers to rethink everything they thought they knew about how galaxies and their central hearts grow in tandem. In the modern universe, we have observed a consistent cosmic law that seems to apply everywhere we look. This rule states that for every 10,000 solar masses of stars in a galaxy, there is roughly 1 solar mass in the central black hole. This ratio is remarkably stable. Our own Milky Way follows it, and so do the galaxies in our local neighborhood. It suggests a symbiotic relationship where the black hole and its host galaxy grow together over billions of years, maintaining a perfect, predictable balance. But when Webb looked at a galaxy from when the cosmos was only 570 million years old, that rule was shattered. Astronomers measured the mass of the stars in this ancient system, and then measured the black hole at its center. The numbers made no sense. Instead of a 1 to 10,000 ratio, the black hole equaled 10% of the entire stellar mass combined. For every 10 solar masses of stars, there was 1 solar mass of black hole. This galaxy broke the universal rule by a factor of 1,000. To visualize how extreme this is, imagine if your own heart weighed 1/10 as much as your entire body. That is the staggering proportion we are seeing in these early systems. The black hole is not just a central feature, it is the dominant force of the entire galaxy. Webb has now found dozens of these objects, which astronomers have given a deceptively simple name: little red dots. In the deep field images, they appear as tiny, crimson points of light against the darkness. But these dots are far from simple. Their distinct red color comes from hot gas swirling into the event horizon of a black hole at terrifying speeds. As this matter accelerates, it heats up to millions of degrees and radiates an immense amount of energy, creating a blazing core that completely outshines the stars around it. The existence of these overmassive black holes creates a massive timing problem for science. In the nearby universe, black holes and stars grow at a similar pace. However, these early galaxies show a completely different pattern. The black holes grew first, and they grew incredibly fast. They became massive before their host galaxies even had time to form many stars. One researcher described it as finding a baby with the heart of a giant. This leads us to the most profound mystery of all. How did these black holes get so big so quickly? Traditionally, there are two main theories. The first involves stellar collapse. When the very first massive stars died, they would have left behind black holes that then grew by consuming nearby matter. But even if a black hole ate constantly at the maximum possible rate, growing from a small stellar remnant to millions of solar masses in only 500 million years requires nearly perfect, impossible conditions. The second, more radical theory suggests that these black holes were born big. Instead of starting as a single dead star, massive clouds of gas might have collapsed directly into black holes without ever forming stars first. These primordial black holes would start their lives already weighing thousands or even millions of times the mass of our sun. Webb's data is now beginning to support this direct collapse scenario. Several observations suggest that these monsters could not have grown from stellar seeds in the short time available. They must have had a head start. Yet, the mystery only deepens when we look at the size of these systems. Little red dots are incredibly compact, packing a tremendous energy output into a volume 100 times smaller than a typical galaxy like the Milky Way. Their spectra are equally confusing, showing signatures of both violent black hole activity and the birth of new stars occurring simultaneously in a tiny space. Are these galaxies in a brief transitional phase where the black hole has just turned on? Or are they a completely different species of cosmic object that we never knew existed? As we map these little red dots, we find they aren't just scattered randomly. They sit within the filaments of the cosmic web, the large-scale structure of the universe. They seem to prefer specific locations where gas supplies are high and interactions are frequent. By studying these law-breaking giants, we are witnessing a chaotic, high-energy era of history where the rules of the modern universe simply did not apply. We are seeing a universe that was much more active, much more violent, and much more mysterious than we ever imagined. Imagine an object with the mass of millions of suns, stripped from its cosmic anchor and hurled into the lonely depths of intergalactic space. The James Webb Telescope has captured evidence of a supermassive black hole racing through the void at a staggering 2 million miles per hour. How can something so massive, which usually sits at the very heart of a galaxy, be cast out like a stone from a slingshot? What happens to the thousands of stars and the clouds of gas caught in the wake of such a high-speed predator for decades? We believe that supermassive black holes were the stable, unmoving anchors of the universe. They sat at the centers of galaxies, governing the orbits of billions of stars with their immense gravitational pull. But Webb has shown us a more violent and chaotic reality by peering into a system called ZS7, located 740 million years after the Big Bang. Astronomers discovered a galaxy with not one but two bright cores. The data revealed gas moving at velocities of hundreds of kilometers per second, swirling in tight, frantic orbits around both points of light. This is the unmistakable signature of two supermassive black holes caught in a deadly dance. They are spiraling inward, destined to collide and combine into a single, even more massive behemoth. This is the earliest black hole merger ever detected in history. The physics behind such a merger is almost beyond comprehension. As these two titans circle each other, they stir the very fabric of space and time, releasing energy in the form of gravitational waves. These ripples in space-time, first predicted by Albert Einstein, carry away orbital energy, causing the black holes to spiral closer and closer together. When they finally touch, the resulting explosion of energy is so immense that it can actually kick the newly formed black hole out of its host galaxy entirely. This gravitational recoil acts as a cosmic engine, accelerating a mass equivalent to millions of suns to speeds of millions of miles per hour. Webb has observed that these high-speed black holes don't just travel alone, they drag a trail of gas and stars along with them. In some systems, the telescope has detected outflows of gas reaching 3,000 kilometers per second, which is more than 6 million miles per hour. This energy is so powerful that it can escape a galaxy's gravitational pull entirely. The impact on the host galaxy is devastating. As the black hole feeds and races through the system, it generates ferocious winds that sweep through the star-forming regions. This process, known as feedback, pushes the life-giving gas out of the galaxy, effectively shutting down the birth of new stars. The black hole essentially stunts the growth of its own home, leaving behind a dead galaxy that can no longer produce new life. In the case of ZS7, the total stellar mass resembles the Large Magellanic Cloud, a small galaxy that orbits our own Milky Way. However, the black holes inside ZZE7 are as large as the one at the center of the Milky Way, meaning they dominate the dynamics of the entire system. Seeing such a massive merger so early in cosmic history suggests that the processes of merging and racing black holes were active almost from the very beginning. Webb's ability to spatially separate these two black holes is a feat of engineering that was impossible before. Ground-based telescopes would see only a single blurred point of light, but Webb's sharp infrared vision allows us to see the two monsters as they prepare for their final, violent union. Through these observations, we are learning that the early universe was not a place of slow growth, but a high-speed arena of collisions and runaways that shaped the very structure of the cosmos we see today. In the deepest reaches of the cosmic dawn, the James Webb Telescope has identified a structure that is currently setting the scientific world ablaze. This is Jades GSZ140, a galaxy that functions like a celestial furnace, forging stars at a rate that seems impossible for its age. While most early galaxies were expected to be dim and quiet, this object is spectacularly bright, so bright, in fact, that Webb could have detected it even if it were 10 times fainter. JADES-GSZ140 sits at a record-breaking redshift of 14.32. To understand what that number means, we have to look at how light travels through an expanding universe. When the light left this galaxy over 13 billion years ago, it was energetic ultraviolet radiation, but as it traveled through the void, the very fabric of space stretched, pulling those light waves apart until they were 15 times longer than when they started. By the time those photons reached Webb's golden mirrors, they had shifted entirely into the infrared spectrum. This galaxy existed just 290 million years after the Big Bang, a time when the universe was only 2% of its current age. The sheer activity within this galactic furnace is staggering. While our modern Milky Way produces perhaps 1 or 2 new stars every year, this ancient system is estimated to be birthing dozens of solar masses of stars in that same time frame. It is tens of times more active than our galaxy, despite being much smaller in size. This concentrated star formation is what creates its incredible luminosity. It is fueled by an abundant supply of pristine hydrogen and helium gas flowing in along the filaments of the cosmic web. However, the discovery of such a bright and active galaxy so early in time has brought us face to face with one of the most significant mysteries in modern science, the Hubble Tension. This is a fundamental disagreement about how fast our universe is actually expanding. Astronomers measure this expansion using a number called the Hubble constant, which tells us how fast galaxies are receding from each other per unit of distance. For every megaparsec of distance, roughly 3.3 million light-years, a galaxy should move away from us at a specific speed. The problem is that the two primary ways we have of measuring this number give us two different answers, and neither side is willing to budge. The first method looks at the very beginning of time. By studying the cosmic microwave background, the afterglow of the Big Bang, scientists can calculate the composition of the early universe and predict how fast it should be expanding today. This method gives us a value of 67.4 kilometers per second per megaparsec. It is a precise measurement based on our best models of how physics works. The second method looks at the local universe. By using standard candles, like Type 1 a supernovae and pulsating Cepheid variable stars, astronomers can measure the distance to nearby galaxies with incredible accuracy. When they combine these distances with the speed at which the galaxies are moving, they get a value of approximately 73 kilometers per second per megaparsec. A difference of nearly 6 units might seem small, but in the world of cosmology, it is a chasm. It suggests that either our measurements are wrong or our understanding of the universe is fundamentally broken. When the James Webb Telescope was launched, many hoped it would be the ultimate tiebreaker. Some scientists speculated that the higher value of 73 was simply an error caused by the instruments on the older Hubble Space Telescope. But Webb has now collected the largest and most precise dataset of nearby supernovae ever recorded. The result Webb confirmed Hubble's findings exactly. The local universe really is expanding at 73 kilometers per second. By ruling out instrumental bias, Webb has turned a potential error into a genuine crisis. This means the Hubble tension is real. If the early universe tells us one speed and the modern universe shows us another, it implies that something changed in the intervening 13 billion years. Perhaps dark energy, the mysterious force pushing the universe apart, is not constant, as we once believed. Maybe it has been growing stronger over time. Or perhaps there is a form of new physics that we haven't discovered yet, something that altered the expansion rate during the Middle Ages of the cosmos. We are at a crossroads where we must decide if we need to modify Albert Einstein's theory of general relativity to account for this discrepancy. The galactic furnace of JADES GSC 14-0 and the stubborn reality of the Hubble tension are two sides of the same coin. They both tell us that the universe is far more complex, more active, and more mysterious than our textbooks ever suggested. We are no longer just observing the cosmos. We are being forced to rethink the very rules of reality. As we reach the final frontier of the James Webb Telescope's current journey, we find ourselves standing at the edge of the ultimate beginning. We are searching for the holy grail of astronomy, the very first stars to ever ignite in the vacuum of space. These legendary objects, known as Population 3 stars, represent the dividing line between a universe of cold, silent gas and the vibrant, light-filled cosmos we inhabit today. These primordial stars were unlike anything we can find in our modern sky. Born from the pure, pristine gas of the Big Bang, composed only of hydrogen, helium, and tiny traces of lithium, they had no heavy elements to help them cool down as they formed. Without this cooling, only the most massive clouds of gas could overcome internal pressure to collapse, creating giants that weighed 50 to 500 times more than our own sun. They burned with a fierce violet-blue intensity and lived short, violent lives of only a few million years before exploding as spectacular supernovae. While these stars have long since disappeared, Webb is hunting for their spectral ghosts. In the outer regions of a galaxy called GNZ 11, which existed just 430 million years after the Big Bang, Webb has detected tantalizing hints of pure hydrogen emission. These patterns match exactly what theorists predict for regions where Population 3 stars are actively forming, if confirmed. We are looking at the original engines of creation, the stars that forged the first heavy elements and made the existence of planets, and eventually life, possible. But as we look at these ancient giants, we are also forced to reflect on our own place in this vast cosmic story. The light we see today left those stars over 13 billion years ago. Since then, the universe has expanded, galaxies have merged, and billions of other stars have lived and died. We are the products of this long, violent, and beautiful history. Every atom of iron in our blood and every molecule of oxygen in our lungs was once cooked inside the heart of a star that Webb is now revealing to us. The James Webb Telescope has shown us that the universe is not just a collection of distant objects. It is a connected narrative. We have seen black holes that dominate their galaxies, like giants with the hearts of babies, and galactic furnaces that birth stars with a fury that challenges our understanding of time. We have witnessed the cosmic web, an invisible skeleton of dark matter that anchors every galaxy in existence, including our own. As we push closer to the Big Bang, we realize that the true scale of the universe is not just measured in light years, but in the sheer complexity of the laws that govern it. We are living through a golden age where the invisible is becoming visible, and the impossible is becoming reality. Webb has opened a window to the cosmic dawn, and through it, we are seeing the very first chapters of our own biography. This is not the end of the journey. It is only the beginning. The universe waited 13.8 billion years to be discovered, and now, finally, we are looking back to the very edge of time itself to understand who we are and where we came from. We are stardust that has finally found a way to look back at the stars. While the James Webb Telescope has dazzled us with the brilliant intersections of the cosmic web, there is another, more haunting side to the architecture of our universe. Between the glowing filaments of galaxies and the massive clusters of dark matter lie the cosmic voids. These are vast, spherical expanses of nothingness, some stretching over 300 million light-years across, containing almost no galaxies, no stars, and very little gas. If the filaments are the highways of the universe, the voids are the true wilderness, the empty spaces where the silence of the cosmos is absolute. For a long time, we viewed these voids as simple, empty holes. But Webb has shown us that the voids are not truly empty. They are home to lonely galaxies that lead a life fundamentally different from those in the crowded neighborhoods of the Webb. In the dense filaments, galaxies are constantly merging, colliding, and being stripped of their gas by their neighbors. But in the voids, a galaxy can evolve in total isolation for billions of years. These void galaxies are like time capsules from a simpler era, because they rarely collide with others. They often maintain pristine spiral shapes that have not been distorted by gravity. Their star formation is quiet and steady, unaffected by the violent shocks of a merger. However, they also face a unique challenge. They are starved of the massive gas inflows that fuel the galactic furnaces we see in the filaments. To survive in the void is to live on a strict energy budget, slowly turning what little gas you have into stars over tens of billions of years. The discovery of these isolated systems is helping astronomers solve a major puzzle in cosmology. Our computer simulations often predict thousands of small dwarf galaxies should exist around every large galaxy. Yet we don't see them in the dense parts of the Webb. Scientists now believe many of these missing dwarfs are hiding in the voids, where the lack of nearby massive neighbors has allowed them to survive without being swallowed up. By mapping these lonely inhabitants, Webb is providing the missing pieces to our map of structure formation. The physics of the voids themselves is equally fascinating, because there is so little matter inside a void. The expansion of the universe actually happens faster there than it does in the dense filaments. Gravity in the filaments tries to pull everything together, slowing the expansion down. But in the void, there is nothing to fight against the push of dark energy. This makes voids the perfect laboratories for studying the most mysterious force in the universe. By measuring how these empty spheres grow and push against the surrounding web, we can see dark energy at work in its purest form. The voids also tell us about the initial conditions of the Big Bang. The size and distribution of these empty spaces were determined by the tiniest quantum ripples in the first moments of time. Every void we see today is a magnified version of a cold spot from the beginning of reality. They are the negative space of the universe, the parts that never quite made it into the spotlight of the Webb. As we look at these lonely galaxies drifting in the dark, we see a mirror of our own cosmic future. Because the expansion of the universe is accelerating, the filaments of the Webb are being stretched thinner and thinner. Eventually, every galaxy cluster will be separated from its neighbors by an ever-growing void, until they are so far apart that their light can no longer reach each other. The universe will one day consist only of isolated islands of light, forever separated by an infinite, expanding nothingness. By studying the cosmic voids, the James Webb Telescope is not just looking at the gaps in the map, it is looking at the ultimate fate of everything. We are learning that the empty spaces are just as important as the stars, for they hold the secrets to the forces that will eventually tear the universe apart. We are seeing the true scale of the silence that surrounds us, and the incredible resilience of the lonely stars that continue to shine within it. As we broaden our perspective from individual galaxies and lonely voids, we encounter a mystery that is both terrifying and awe-inspiring. Our entire corner of the universe, including the Milky Way and all its neighbors, is not sitting still. We are being pulled across the cosmos at a staggering 1.4 million miles per hour toward a specific hidden point in space. This invisible destination is known as the Great Attractor, a massive gravitational anomaly that is essentially acting as a giant magnet for hundreds of thousands of galaxies. How can something so immense, with the power to move entire superclusters of galaxies, remain hidden from our view for so long? What lies at the heart of this gravitational anchor, and what happens when we finally reach it? The mystery of the Great Attractor has baffled astronomers for decades, primarily because it sits in a region of the sky known as the zone of avoidance. This is the part of space hidden behind the thick, dusty disk of our own Milky Way galaxy. For years, our visible light telescopes were completely blind to this region, unable to see through the curtains of gas and stars that make up our galactic home. We knew something massive was pulling us, but we couldn't see what it was. This is exactly where the James Webb Telescope has changed the game. Because Webb is an infrared specialist, it can do something that visible light telescopes cannot. It can peer through the dense dust of the Milky Way. Much like smoke clears when viewed with thermal cameras, the gas and dust that hide the Great Attractor become transparent in the infrared spectrum. Webb is finally allowing us to see the massive structures that are responsible for this cosmic tug-of-war. What we are finding is not a single object, but a colossal concentration of mass, a supercluster of galaxy clusters. The Great Attractor is the gravitational center of our local supercluster, a structure named Laniakea, which means immense heaven in Hawaiian. Laniakea is a vast network of hundreds of thousands of galaxies, spanning 500 million light-years, all flowing toward the same central point. It is a brilliant example of the nodes we see in the cosmic web, a place where the invisible filaments of dark matter intersect and pool together, creating a gravity well so deep that nothing in our region of space can escape its influence. However, even as we move toward the Great Attractor at millions of miles per hour, we may never actually reach it. This is because of the relentless push of dark energy that we discussed earlier. While the Great Attractor's gravity is trying to pull us in, the expansion of the universe is pushing galaxies apart at an even faster rate on the largest scales. We are caught in a cosmic struggle between two opposing forces, the pull of local gravity and the push of global expansion. By studying the Great Attractor through the lens of Webb, we are learning about the flow of matter in our universe. We are witnessing how the largest structures in existence organize themselves and how the invisible skeleton of dark matter dictates the motion of every star we see in the sky. It reminds us that our galaxy is not an island, but a small traveler in a much larger, dynamic current that is shaping the destiny of the entire cosmos. We have traveled from the golden mirrors of a machine floating 1 million miles away to the impossible galaxies that formed when the universe was still in its infancy. We have witnessed black holes that defy the laws of physics and the vast invisible web that connects every star in the sky. Now, in this final chapter, we reach the ultimate destination of our cosmic journey, the search for the very first stars to ever ignite in the darkness, and a reflection on what this vast story means for us, the observers. Before the first star was born, the universe was a place of total shadow, an era known as the Cosmic Dark Ages. There were no galaxies, no planets, and no light, only vast clouds of neutral hydrogen and helium gas created in the fires of the Big Bang. For hundreds of millions of years, gravity worked in the silence, pulling these pristine gases together into massive, dense clumps. Because there were no heavy elements like carbon or oxygen yet to help the gas cool, these clouds had to be immense to finally collapse under their own weight. The result was the birth of the population 3 stars, the true ancestors of everything we see today. These were not like our sun. They were celestial titans, weighing 50 to 500 times more than our home star. They burned with a fierce violet blue heat, shining with a brilliance that transformed the universe from a dark void into a realm of light. They were the first engines of creation, and their mission was as brief as it was vital, because of their enormous mass. They lived for only a few million years before dying in cataclysmic explosions. It was in these final, violent moments that the first heavy elements were forged. When these primordial stars exploded, they scattered the carbon, oxygen, and iron they had created into the surrounding space. This was the most important moment in history. Without the death of these first stars, there would be no rocky planets, no water, and no life. We are quite literally the children of these ancient giants. Every atom in our bodies was once cooked inside a furnace that burned 13 billion years ago. The James Webb Telescope was built specifically to find the spectral ghosts of these stars. While we have not yet captured an image of a single population 3 star, Webb has found tantalizing evidence of their existence in the outer reaches of ancient galaxies. In systems like GNZ 11, Webb has detected signatures of pure hydrogen gas that match the predictions for regions where these first stars were active. We are closing in on the moment of cosmic dawn, the second when the universe first turned on. But as we look back at the edge of time, we must ask ourselves, what is our place in this staggering scale? We are inhabitants of a small, rocky world, orbiting a middle-aged star in the suburbs of a typical spiral galaxy. To the universe, we are infinitesimally small, Yet, we are the only part of the universe that has developed the ability to look back and understand its own origin. We have built machines of gold and beryllium to catch photons that have been traveling since the beginning of reality. Webb has revealed that the universe is far more mature, more active, and more crowded than we ever dared to imagine. We once thought we were looking at a simple, slow-growing nursery, but Webb showed us a masterpiece of complexity that was already in full swing hundreds of millions of years after the Big Bang. The Hubble Tension and the little red dots remind us that there are still fundamental mysteries about how space and time behave. Our textbooks are being rewritten in real time. The story of the universe is a story of transition from darkness to light, from simple hydrogen to the complex chemistry of life, and from chaos to the organized beauty of the cosmic web. We are part of that transition. The James Webb Telescope has pushed our vision to the absolute limit, showing us that the scale of the universe is vaster and stranger than any fiction. As the telescope continues to stare into the deep infrared, it will continue to uncover secrets we haven't even thought to ask about yet. This is not the end of our discovery. It is the moment we finally opened our eyes. We are a way for the cosmos to know itself, and through the golden eye of Webb, we are finally seeing the true face of our home.